My days are coming. In fact, they're not sacking me until I'm about to retire. So they'll just hold their breath and I'll go. But I discovered, so I'm a theoretical physicist basically, but recently I've been doing experiments because the experimentalists do not dare do because they would lose their jobs. And so I'm doing both jobs at the moment, being a theoretical physicist and an experimentalist. And so I'm going to tell you about just some of the experimental data that's relevant to this whole business of the fundamentals of physics. Because basically physics went wrong 105 years ago, in fact a bit earlier than that, as you see. But in terms of theory, it went wrong in 1905 in a massive way, and physics has never recovered from a huge mistake that happened in 1905. You know what I'm talking about. You know how popular I am now in physics. I'm an untouchable physics in Australia. All my old colleagues don't want to know. Don't talk about Cahill or what he does. It's just impossible. But let me show you the data. Because the data is what keeps physics honest. That's why most of the state is suppressed. You cannot publish it in a major journal because it contradicts the belief system of mainstream physics. So if you want to please have a chance to read that. So let me move on. It's about relativity. I just want to emphasise what relativity is about. If you have two observers observing some events up here, these are the sort of events you can look at. Some speed of radio waves, light, length of rods that are moving past the observers, things like that. And each observer makes his own measurements using the same protocols. Then how you relate the data from this observer to this observer is a problem of relating. And that's where, of course, the word relativity comes from. It's the theory of how the data will relate from one observer to another, one experimentalist to another. And I'm sure you knew that, but I just wanted to emphasise that. And the other key part in physics is there are two kinds of activities in physics, theories and experiments. And they feed on one another. It goes both ways. And it's a very slow process because you need a theory to do an experiment. The experiment may not work the way you think it does, so that sort of comes by and feeds back on the theory. And we go around this loop, and we've been going around this loop for about 400 years, and basically we still haven't settled down on a theory that's consistent with the experiments. Physics is the slowest moving science that we know about. All the other sciences get it a lot easier. And it's a sort of a philosophical question as to why physics has so much trouble moving forward. So, you can cut across. So, here's a summary of the major relativity theories. The first one was by Galileo, as some previous people mentioned. And one of the things that comes into all the relativity theories is what you understand by space and time. And then all the other phenomena sort of are living in this space-time thing. And Galileo came along. That guy was just horrendously talented. He started physics, basically. And he modelled space as a static piece of three-dimensional geometry. And of course what happens is that physicists always borrow mathematical structures from mathematics. So he borrowed Euclidean geometry from Euclid. And you know, you have all the properties of triangles and straight lines and points in the geometry. In time, he modelled as a piece of one-dimensional geometry, the timeline, which we all use without too much thought. And in this one here, rods and clocks are unaffected by the motion through space. We're hinting at the so-called relativistic effects. So there are no relativistic effects in Galilean relativity. Then after the Michelson-Morley experiment, I'm going to have quite a bit to say about that. After the Michelson-Morley experiment, this guy, Lorentz, who not only was an incredibly brilliant physicist, but also a very ethical physicist. He wasn't out there promoting his name as some of the other people here I can mention. Lorentz was responding to a slight misunderstanding of the Michelson-Morley experiment that he had. And I'm going to tell you about the Michelson-Morley experiment. And he said that space is a static bit of three geometry, and there's something called the ether that moves through that space. So this is a dualism model about space. And time is still one-dimensional geometry. And rods are contracted by motion through space, and clocks are slowed by motion through space. And the speed of light is c in vacuum relative to space. So that was Lorentz relativity, 1892. And of course, he almost got it. And then we come to the next chap, Einstein, also responding to the Mach-Moore experiment after Lorentz. And he declared that space does not exist. In special relativity, there's no such thing as space. There's no entity, that's what you call space. There are all sorts of perspective effects where each observer has some sort of notion, sense of space, but the spaces that different observers seem to use don't belong to some entity that's independent of them. It's purely what's called a perspective effect. He also said, this in 1908, time does not exist. And what, of course, you all know what he did. He invented this four-dimensional space-time. And rods are now contracted by motion relative to the observer, which is different to what Lorentz has conjectured. Clocks are slowed down by motion relative to the observer. And the light speed is c relative to all observers. So every one of these statements here contradicts the Lorentz model. So these two theories are in fierce opposition, although if you look up the web, you'll find that they're regarded by most physicists as being equivalent. And then there's Neo-Lorentz. This is really my work, but I'm paying respect to Lorentz's thing. And what it says is, and this is the evidence and the data that I'm going to show, space is actually a dynamical complex system. It's not a piece of geometry. Up here, this is meant to be just a geometrical thing. Space is actually a complex dynamical system. And you're going to say, how do you know that? Well, I'm going to show you how you measure that and detect it. And the geometrical parts, that's three-dimensional, is only sort of above a certain scale. Below a certain scale in size, the space doesn't even have geometrical properties. It's just a foaming structure. The ether does not exist, you don't need that. Time is a process, not a piece of geometry. Rods are contracted by motion through space, checkable by experiment. Clocks are slowed by motion through space, checkable by experiment. And the speed of light is c relative to this dynamical complex structure. So you see, these are all very different relativity theories. And the best way to do physics is to have competing theories. It's like playing football. You can't play football with one team. You've got to have an opposing team. Okay, otherwise you can't score. And so, and this was, and the other difference that I should point out is back here, rods are contracted by motion relative to the observer, but Einstein went further. Any spatial distance between points in space is also contracted. Board already? Thank you. That's how you do it? Okay, I remember that. Whereas in Lorentz relativity, rods have to be physical objects. Only physical objects are contracted. Only clocks are retarded by motion through space. Einstein had a much more different theory. So that's the sort of the background. And here's a little bit of the, I like to give the summary first, rather than wait to the end, just in case you leave. Space exists. It actually is a concept that was banned by the cult of Einstein. The cult of Einstein is the world of academic physics that I belong to. In that, they believe him, absolutely believe him. And you're not allowed to challenge any part of that physics. Dynamical space, it turns out, was detected first of all in 1887, the famous Mach-Moore experiment. I'm going to show you the data. Space as a dynamic system has been missed by physics from the very beginning, 400 years ago. And there's a theory to this space that's actually very trivial to set up, and it's been extensively tested against a whole lot of phenomena. No flaws yet. It gives a new explanation for gravity. It turns out gravity and the quantum theory have now been unified. You won't find that in the mainstream journals, but it's happened. Okay? Gravity is a quantum effect, and it's actually the refraction of what we call the matter waves. Black holes are predicted by the theory, and they're everywhere, not just at the centres of galaxies or whatever. Black holes are just a common phenomenon, and there's experimental evidence all over the place. Early experiments, if you go back to Marcus and Morley, the Miller experiment, what you notice is they were picking up wave effects. And these are the gravitational waves that actually exist, not the ones that they're looking for down at LIGO, down in Louisiana and so forth. These are the actual waves that exist and have been seen again and again for 127 years. Down at LIGO, they don't know that, because we're talking about what's gone wrong at LIGO. I spent the last 10 years developing various space detectors. The early ones were complicated interferometers like the Michelson interferometer, like the Miller interferometer, and various other experiments. And I tried various ways, trying to get it simpler and simpler. And we now have a very compact and robust and sensitive gravitational wave detector. And I brought one along. This is a gravitational wave detector. It costs you $20. There's no reason why you can't go home and do. You need 2 of these to measure the speed of the gravitational waves. I'll show you the data, how it's done. And all you need is an oscilloscope to compare the output from this. I'll show you the circuit for this. This has a battery, a resistor, and some diodes. There's nothing. Oh, you want to see the design?
Reverse engineer.
You're reverse engineer, right?
No, it's for.
Now, academic physicists have refused, in my presence, to complete this construction experiment. They're terrified of the mafia in physics because if they know what the mafia will do to them if they're caught repeating the experiment with this device. So I know a couple of people who repeated the experiment, but one of the people who repeated the experiment with this device was a high school student in Adelaide, in Australia, where I come from. A high school student has done the experiment and confirmed the results. It's the most trivial experiment you could do. The principle of this contradicts every part of physics. It contradicts space-time, Einstein space-time. It contradicts the gravity theory, and it contradicts much of quantum theories. So this is the foot in the door of, I think, the next era of physics, because it contradicts all the things that I used to teach. I'm as guilty as hell of propagating nonsense. I'm waiting to be sued by a whole lot of ex-students.
What is the speed of the gravitation wave?
I'll come to that, if you can hold. Okay, wait till I'll show you the data.
So did you get paid for teaching nonsense?
Which nonsense? This one or the one before?
The one before.
I got paid for it. Oh, it's excellent. I could convince students about the beauty of special relativity and general relativity.
Oh.
I worked in particle physics for a long time, where it's based on special relativity, quantum field. I was an expert. I've had enormous number of PhD students in particle physics based on special relativity. I had a moment of self-discovery in 2002 when I realised that the Michelson-Morley experiment was far from none. I put a paper out there, and within 24 hours I was excommunicated from the world of physics. I got an anonymous email from the archive saying, "You're stuffed." They didn't use that word, I can't remember the polite way of putting it. They said, "You are stuffed." And ever since then, the world of physics said, "We don't want to know about it." But I'm going to show you the data. And of course, this will destroy your lives too. It's so simple. So,
You can take off the microphone.
sorry. So here's let's talk about the most profound experiment in physics was the Michelson-Morley experiment in 1887. And I haven't got a photograph, I'm sure many of you can see, but this is the one that Miller did some 30, 40 years later at the top of Mount Wilson, which is a couple of miles away from the Jet Propulsion Lab. There's something very significant there. What comes out of the Jet Propulsion Lab is inconsistent with what Miller discovered on top of Mount Wilson in Alaska. So this is the Michelson-Morley device. In itself, it was a brilliant discovery. And but he never understood how it works. I only discovered how the Michelson interferometer works in 2002, and when I published that, that's when they said, shut him up. Because Michelson-Morley, as you all know, reported a null effect. And that bundled analysis by Michelson and Morley led to the Einstein relativity theory. That's the history of physics, as you know. And we know that Einstein knew about the Michelson-Morley experiment, although on different occasions he had different versions of the story. But there are papers that were recently sold at auction where he wrote to one of the visitors who destroyed the reputation of Miller, saying thanks very much for doing that. Because if these guys were seeing non-null results, then his theory was dead in the water. That exchange some option risk. Anyhow, the Michelson-Morley experiment, I know some of you have seen it already. You send light in here, you split it into a beam going this way and one going this way, reflect it at a mirror. The light beams come back, they interfere, and you get fringes across this detector right here. And as you rotate, the time, and the idea is if the speed of light is different in different directions, as you rotate, the time to go out here and back will be different from the time to go out there and back. And because of just the simple geometry, as you rotate it, fringe shifts should move backwards and forwards. That was Michelson's idea. What we know is that the fringe shifts were much smaller than Michelson had anticipated. That's why he finally declared it to be a null effect. Even though if you read the paper, he talks about the speed of the anisotropy effect. He got a maximum speed of 10 kilometres per second. He said, oh, that's too small, I'll forget about it. Turns out that was a key effect that he should have reported a little bit wisely. But in excuse for Michelson, physics had never been through a revolution, a paradigm shift where you throw away the old theory and have a new theory. This was a pre-paradigm shift, and no one knew about paradigm shifts in this area of physics. And so Michelson believed whatever the current theory was. And anyhow, this is the theory of it. This is the difference in travel time between the arms, delta t. The length of the arms out here come in as L. Speed of light comes in. V is the speed of something going through the apparatus. In the old days, they thought of it as the ether. That will correct that. And here's just the angle dependence. As you rotate the device, there's an angle effect. And the most important thing that screwed up physics for the last 100 plus years is this coefficient out the front, which is what you call the sensitivity of the apparatus. It's the calibration constant. Every device you build has got to be calibrated. This was the first one, and Michelson calibrated it using a theory. What theory did he use? He used Galilean relativity. In Galilean relativity, K has a value 1, if you go through the whole theory. And so he was, and then if you come down to Einstein said as you rotate there are no fringe shifts, so Einstein has the value K squared equals 0, no fringe shifts. So Galilean relativity gives K squared as 1. Einstein relativity gives K squared as 0, no fringe shifts. If you use Lorentz relativity, you get K squared as n squared minus 1, n squared minus 2, where n is the refractive index of the gas that's sitting there in the light particles. It turns out there's an incredible design flaw in the Michelson interferometer. It only worked because there was a gas present. And the reason for that is that there are two effects operating. One is the Lorentz contraction, which we can prove actually happens. And the other one is the sort of the geometrical effect that Michelson was aware of. And in the Michelson interferometer, those two different effects just happen to accidentally cancel. And the only way to stop the cancellation between the two different physical effects is if you have a dielectric there. And historically, there was air, there was gas there. Fortunately, in this period, they didn't have vacuum pumps. Later, the physicists invented vacuum pumps, and now they always use vacuum pumps when they do the Lorentz, when they do the Michelson interferometer experiment. They see nothing. They pump out the air, but the air's got to be there. Anyhow, so for air, the refractive index, which is the speed of light over the speed of light in vacuum over the speed of light in the gas. For air, it's very close to 1.00029. In vacuum, it's 1. So in vacuum, n squared minus 1 is 0. So if you do this experiment in a vacuum, which Michelson didn't do and which Miller didn't do, in a vacuum it won't work. In air, you find out that this instrument is incredibly insensitive because you've got n squared minus 1. Well, if you square that and subtract 1, you get some incredibly small. So the Michelson interferometer is fundamentally incredibly insensitive to what they were looking for. Okay? It's about 2,000 times less sensitive than the Galilean relativity would predict.
You also have a heat assumption.
Heating?
Heat assumption.
Hidden assumptions.
Which one?
You assume, you discard the fact that the generative gravity will affect the speed of light.
No.
You assume there's no gravity.
Yeah. And well, I'll show you the data. Yep.
You'll get a value of those couple of elements from this, as you say.
Yeah.
I thought they were looking for 30 kilometres per second, and they actually found about 8 kilometres per second.
Yes.
So a quarter as much.
Yeah. Hang on. Don't use up my jokes. What you're telling me is all the confusion that's in physics about this experiment. Here's the data. Right? Here is the data from the Michelson-Morley experiment. Here's the Michelson-Morley, sorry, which one is it? The bottom one. Here's the Michelson-Morley, one day in July 1887. It consisted of, how many rotations did Michelson? 6 or something, was it? An average of over 6. So we do a rotation over about an hour. Here are the friendships that you get from the Michelson-Morley paper, which anybody can access on the web. And what I've done here is no more than what Michelson did. You've got to correct for temperature effects, and you also got to correct for the fact that there is under the Higgs effect. And what you get left over is this incredible curve, and it's got this almost exact cos to theta angle dependence. This is the angle as you rotate the device. This is incredible data. These are just statistical differences between the actual data, the root mean square difference between the actual data, which is one of these lines, and the theoretical one you expect to see. Okay, and Michelson never did that, and a mistake he made, which Hector pointed out, he averaged the data from different days, and the data fluctuates enormously from day to day. This flowing process is not a uniform, smooth flow. It's very turbulent. And every experiment that's ever, sort of all experiments that followed that worked, all picked up the same intense fluctuations. Anyhow, so this is the data, and Michelson could have published this. He would have had that data if he hadn't have averaged the data over successive days at the same time. So this was the biggest stuff up in the history of physics. We're still living with the consequences of Michelson not quite doing his data analysis correctly. Now, Miller was a junior physicist at Michelson's University in Cleveland, Ohio. He knew that Michelson had stuffed up the analysis. Michelson hated Miller because he didn't believe in Michelson. And there's a bit in one of Michelson's books where he says one of the things he wants to prove was that Miller got it wrong. He had personal agenda against him. So Miller, over a long period of time, developed a much bigger interferometer, took it up to the top of Mount Wilson because they thought there was an drag effect, and there was all that sort of stuff going on at the time. And here are the friendships on one rotation, averaged over a number of rotations, but through 360 degrees. And again, and what you do is you take that expression I had in the previous one, you've got the length of the arms, the speed of something go past, and also the angle comes in. And Michelson-Morley, when you do that, you get a speed of 551 plus or minus 33, which is the error path. This is the speed of something going past the apparatus. And that was answering your questions. It's not 30. The Michelson-Morley experiment gives you a speed of that. And it also gives you that whatever's happening is coming from basically roughly 20 degrees within the due south. If you go up here to the Miller experiment, which was done in 1925-26, you get a very similar speed, 480 plus that. It also coming from the south, almost the same. And these were about 40 years apart. And this is a highly dynamic process here, so you don't expect the same numbers of them. And this is a plot of this direction. Here's the south celestial pole. And this is declination is measured this way. That's just like longitude. And this is right ascension, which is the astronomer's version of declination is like latitude. And right ascension is like longitude. And what Miller discovered was that the average direction was here. It's got a right ascension of about 4.5 hours and a declination down, this sort of thing. This is the average But over the various months in which you collected the data, the direction of the flow of whatever this is, something's flowing through the apparatus. It changes like this, and this is the Earth's orbit effect. But that's a small effect. That's the 30 kilometres per second. This is a massive flow going through the apparatus. This blue one I'll show you in a moment. Of course, the world went ballistic against Miller, and no one wanted to know him. Einstein went on about how he did it right, and other people said it was all wrong. And then what happened was, there's an interesting story here, when Miller died in the 1950s at Cleveland, Ohio, they slammed the door in his office, in anger, I suspect. Because by that stage, Michelson had won the Nobel Prize. Basically, for this experiment, although the Nobel Prize didn't identify that. Anyhow, they slammed the door in the 1950s on Miller's, and a chap who you might know, James DeMayer, who works on writing, he went up there and he sort of said, what happened to all the Miller data? He collected an enormous amount of data. Michelson collected very little amount of data, just a few tables in his paper. And he went up there and they said, oh, no one's ever been in Miller's office since he died 40 years ago, or 50 years ago, yeah, or more. So they went down there and opened the door up, and his lecture notes that he was preparing as he died was sitting on the table, his coffee mug was sitting on the table, and up on one of the shelves was a huge box of all the data that he collected over 2 years. It had been sitting there for 50 years, untouched, collecting dust. Anyhow, the university quickly decided to file it away. James DeMayer got a copy of all that data, photocopied all the pages, and these are A4 sheets, all handwritten. And James DeMayer got hold of a copy of that, and he photocopied it and sent it to me, because I was sort of looking at this stuff. Yep. So anyhow, all of this data here is totally inconsistent with special relativity. There should be no friendships, but they were always there in the data, and they were there in the Miller data. No one, but everybody claimed that these guys didn't know what they were doing, particularly Miller. And so this contradicts Einstein's special relativity, because basically what it's telling you is the speed of light is different in different directions, and in one direction it's 500 kilometres per second faster, roughly speaking, than 300,000. And in the opposite direction, it's 500 kilometres per second slower. There's a difference of something like 1,000 kilometres per second between the two ideal directions. This has been available in the historical records of physics, except they're locked up for safekeeping. Okay? So this is incredibly dramatic. And as someone said earlier today, you only need one good experiment to kill a theory. Agreement between theory and experiment doesn't prove theory, but one clear-cut, two experiments showing the same results kill off the Einstein theory. And when I pointed this out in 2002, the only person that killed off was me. Okay? But I'm very tough-skinned, okay? It doesn't worry about it. Actually, in physics, it's nice to be known you hate it, because it means maybe I'm doing something interesting.
I think you are doing the experiment right, but your interpretation is wrong.
Okay, whatever. Whatever.
Why is wrong? Because Michelson model shouldn't have a zero difference.
So what difference?
The Michelson model protrusion preliminarily is not because the gravitational effect has not been hung on.
Well, you have to prove that the gravitational effect would have been large.
That's precisely.
I disagree with you, by the way.
Pardon?
I disagree that the gravity is important.
You can disagree, but I can.
You can disagree with things. That's okay. I've got a feeling that there's a lot of this going on. That's why.
What you prove?
Hey, look. Wait till I show you all the other data.
Let me repeat. Your data is right, but your result shouldn't be zero. Your assumption the result should be zero. That's wrong.
No, I didn't show you relativity. Relativity says it's zero.
Relativity is assumed the ideal case. This is not ideal
So
case.
you're defending special relativity?
Yeah.
Oh, okay. We understand. I won't put my back towards you.
Yeah, I'm defending relativity.
Is that direction significant, like for motion around the galaxy?
I was waiting for someone to ask that question.
Oh, good.
This direction is not It's got the right ascension that lines up with the centre of the galaxy, but the declination doesn't. It's sticking out of the plane of the ecliptic. And I've never been able to find some explanation for why that might be. But this stuff we're observing here, this is a galactic effect. And our galaxy is one of the group. And so, you know, so it's a very complicated business as to why it's pointing in a different, but I don't know why it's pointing in this direction.
What about our motion back in terms of the cosmic microwave?
And it's not related to the cosmic microwave background. It's unrelated. It's a different speed, a different direction.
Yeah.
It's an unrelated phenomenon.
So you're not right.
Okay, well, let him
I mean,
speak.
you
He has a lot of data.
I can handle this.
Misinterpret the thing.
Let him speak. Let him finish.
Your experience is right.
Let him speak.
Data is right, but
Okay.
your interpretation is wrong.
It's okay. It's okay. Now, here's the Marx and Morley data over against sidereal time. And this is the speed that you get. I showed you some of the speeds there, roughly around about 500 or 400. This is the Marcus, these light blue ones are the Marcus and Morley data at about, one of the experiments was done at 7 hours local sidereal time, the other one was sort of like 13 hours, 6 hours later, local sidereal time. And there's reasons for that. In one case, the Cleveland was moving parallel to the Earth's orbit motion, and in the other case, the apparatus was aligned at 90 degrees to the Earth's orbit motion. So it was doing the right idea. And one of the numbers I gave you was up here at 525. Well, that's the maximum up here. But if you average his data over successive days, you get an average here and a variation. Over here you did that. But notice how little data Marcus had. After he saw did the experiment and realised the effect was very small, basically walked out of the lab.
Yeah.
And didn't go back to the apparatus.
And also,
Let him speak.
Einstein had never carried his theories based on Michelson model.
I'm sorry, it's just been published or sold letters from him to Shankman saying thank you, because I did get the idea from the Marx and Morley experiment. But there's different versions of that story because Einstein never told the same story about the history of this. He had a different story every time he spoke.
Einstein never say his theory rely on the Michelson model.
His story
You did. I'm sorry, I can contradict you.
Let him speak.
Anyhow, this other data, the other data here is from the Miller experiment. He just collected an enormous amount of data. He did the experiment over 4 different months of the year and every day of those months. And when you, and this is just the data for September of 1925, I think it was. And what you notice is that it's very, tremendous amount of fluctuations in it. And this is what you expect to get if there were no fluctuations in whatever it is that's causing these effects. And what you notice is that the fluctuations are very large. And everybody said, well, that's just because Miller didn't know how to do the experiment.
Isn't this the type of thing that people say so that you need enough data to be statistically significant? Isn't that basic stuff?
Oh, well, don't forget, he did it for 4 different months, and that's how he got that right ascension declination plot. And he worked very hard at doing that, and it was all done by hand. So, but these are just the early experiments. I'm going to show you how to do this experiment for $40. Okay? So, this is the history of it, and what it shows is the intensity of the fluctuations, assuming they're real and not artifacts. Based on any one experiment, you can't make any deductions. That's your point. It could have just been a tea lady walking up and down the corridor with a trolley or something. These are very sensitive instruments, and that when both those instruments were floating on tanks of mercury, cut out vibrations and things like that. So they're very difficult experiments to do, and you have to take data for months and months on end. Michelson can do. So you can sort of work it out. This apparatus here takes about a minute to collect all the data you need. So when I was aware of that, I decided I'd be better to become an experimental physicist, because no one else is ever going to develop this. Here's another chap who did an experiment. His name was Roland DeWitt. He was a telephone technician. He wasn't an academic physicist. He was a telephone technician in Belgium. He was working for the Belgicom company. and he worked in their sort of central laboratories as a technician, and he sent radio waves, RF 5 megahertz radio waves, up and down the coaxial cables between two laboratories that this company had in Brussels, and he measured the speed of the radio waves down the cables. I won't go into all the technical detail. It's a very tricky experiment. Temperature was controlled by the fact that the cables were well buried under the streets of Brussels. And what he did is that he plotted against sidereal time. He consulted astronomers and said, "Oh no, you've got to look at the sidereal effects." Here's the difference in travel time in nanoseconds for radio waves going down these 1.5 kilometres north-south orientated coaxial cables. And here's the, and this is like upside down, it depends on which way you want to measure the time difference. But again, you see the same right ascension that you get from Miller, from Michelson, and now here's another guy in 1991, the next guy to do it. And again, it's in phase with the sidereal effect. So it's a direction that's the same as Miller got. And amazingly, DeWitt never knew about Miller. So it's one of these blind experiments. We know he wasn't faking it. And what you again see are wiggles, fluctuations. Again, it could be noise, electronic noise, temperature noise, or whatever. Again, one experiment doesn't prove that it's well done. Again, it would appear on the face of it that this contradicts relativity because the speed of the radio waves down a coaxial cable should not depend on the orientation of the cable relative to the stars, which is what right ascension is measuring. Okay? What do you think happened to him when the company found out that he was putting out paper with that as the conclusion? He got the sack. Got a pink slip at the end of the week. Get out of this place. And then around about 2002, I was trying to contact him. I contacted by his email address, by written mail. Finally, I had a friend in the UK who went across, Thomas Goody, some of you might know, because he's very much involved in the LA effect experiments, mate of mine. He went across to Belgium to try and went to the family village to find out what happened to Roland. Because I wanted his data. He had 6 months of incredible data, not just a few rotations that Michelson had done. So he went out to the village, and sadly, he would have taken his own life. Just before I was trying to tell him that this was one of the great experiments of the 20th century. The Miller experiment and the DeWitt experiment were one of the two most significant experiments of the 20th century in physics, as far as not my opinion, obviously you disagree.
No, I'm not saying
that's
that.
okay. I didn't want to provoke you.
It's wrong. I didn't say the experiment is wrong.
Only the interpretation.
Yeah, okay. So let's move on, because if there's a real effect going on here, you should be able to measure it by a whole lot of different techniques. Okay, you just don't use interferometers, because maybe there's something funny about them you don't understand. Here's another way of doing it. This is called the flyby Doppler ships, which has been mentioned quite a few times. And what NASA does, NASA collects the data. You bring in a spacecraft, you do a flyby, and you fling the spacecraft out into the direction of the outer planets. Here's one of them called Galileo, which is quite appropriate. And here it's sort of it's a cartoon thing, but it shows Galileo actually not that far out above the atmosphere doing this collection for the Doppler ship, indeed gives you the speed of the spacecraft. Now, NASA can measure this because you're only measuring frequencies and you've got atomic clock. NASA could measure the speed here down to millimeters per second for spacecraft. These are doing 10,000 kilometers an hour, and NASA can sort of measure them to millimeters per second, which is absolutely fantastic. And what they noticed 20 years ago, as they started to do these flybys, is that the incoming speed asymptotically was different to the outgoing speed. So this is the flyby model. The speeds of in is not the same as speed out. And the NASA people finally decided that there was another force acting. One force was electromagnetism, nuclear,
Exactly right.
gravity, and then they had a weak force, and then NASA decided there was another force.
Yeah.
Got published in Physics Review Letters,
Correct.
very significant paper. And what they always say, the energy of the spacecraft has, I can't remember, it's increased or decreased when it goes past the Earth, and it's asymptotic. However, if you use the Lorentz relativity, the speed of the radio wave, because this assumes the speed of the radio wave is the same in all directions. Okay? They assume that.
The measurement is based on C being constant in all reference.
In all reference, yeah. And if you assume the Lorentz relativity, or just Lorentz relativity, the speed of light is different by v.
Stop doing this.
And here and here, and this is the change in the direction of these two asymptotic trajectories relative to the direction of the flow. And they reported that this anomaly is 1 part in a million. So they're working with incredible precision. Only NASA has the money to do this experiment and measure it to that precision. 1 part in a million, but 1 part in a million is like 300 kilometres per second over 300,000 squared. So you've only got to read the paper and realise, hang on, this is a this is not a relativistic effect.
Can I comment?
No.
Oh. After we'll have questions. After the presentation.
So what you do, and there were about 6 flybys. There's been some more since I had the data. And this is and what you can do is you do a best fit to all the flyby data, straight out of the physical review lens NASA paper, and you try and explain the data by choosing a speed and direction for the anisotropy of the speed of the radio waves. And when you do that, you get 500 kilometres per second as the speed, and you get a direction, 4.29 hours right ascension, destination minus 75 degrees measured from the equator, at the Earth equator. Same number, basically, that you get from analysing the Michelson-Morley experiment. Same speed and direction from the Miller. Same experiment now from the NASA data. Totally different device. Not only that, because the NASA data is so precise, you can pick up the orbital speed of the Earth. That is why you get this, what's called by Miller, the aberration. So here's a flyby in August, 1 in December, 1 in January, and 1 in March. And the fact that the direction of the preferred speed of the radio waves changes over years because of the orbital effect. We're looking at this from an orbiting laboratory. You can pick up that there's a component of the flow that's about 11 kilometres per second into the surface of the Earth. You can also pick up from the data that there's a flow towards the Sun of about 42 kilometres per second at the distance of the Earth. So because the data is such high quality, you can dig into it and do quite precise fitting. The NASA data now agrees with all the previous experiments and also contradicts relativity. But it's still not enough. Right? Relativity will survive for another 50 or 100 years. I don't expect to see it ever nudged out of the way. And as Poincaré said, physics moves forward by funerals. You've got to wait until the true believers die. So here's another one. So I did that. Well, I did contact NASA people who wanted it, and they didn't want it. Whoops.
Does that come from just one flyby, or does that come from multiple different ones?
Multiple.
Is that all done from one flyby?
No, that's 6 flybys. That's why it's got different data at different times of the year. I've lost it. I'll hit the wrong button somewhere. Thank you. So, now I just want to mention to you, there's a dynamical theory that undergraduate level stuff. I teach this stuff at the university to second, third, and fourth year students. Now the dean doesn't approve of it. I've been told to teach physics as it's in the textbooks. Do not corrupt the students. Anyhow, this is how you derive the theory. It's really dead easy. Newtonian gravity, we all know about the inverse square law. You introduce this acceleration of matter, little g. People have been talking about that. Newtonian gravity can be, this is a gravitational field, the matter acceleration field, and it satisfies a little equation. The divergence of g is given by the Newtonian constant and the density of matter. And you've got to have the curl in here if you want to stop rotation effects. What you do to discover what's going on here is instead of talking about this equation, you put in here, instead of the acceleration of matter, you put in the acceleration of space. This is the acceleration of space of any fluid. It's just a generic form that follows from simple calculus argument. It was discovered by Euler, who was around not long after Newton and was working on fluid mechanics. So this is what's called the Euler effect. And the acceleration is more than the rate of change of v. It's got this term here, which is what's called the collective or constituent component. And you put that in here instead of g. So what you've now got is a differential equation for a velocity field. And if you believe that, and what you're saying is this velocity field is more fundamental than the g field. Gravity field is a higher level phenomenon. That's how matter responds to space. Whereas this is about how space behaves. And basically this theory says that matter tends to destroy space and flows into space, into matter. If you go to the Schrodinger equation, here's the simple Schrodinger equation with no external forces. What you have to do is, for the first time, you've got to put into the Schrodinger equation that space actually exists. Schrodinger didn't know about that. And there's a unique way to do this. There's only one way to put this space term in here. It's the d dot grad, which differentiate divergence of that. And you put that in, and then you do a wave packet analysis. Matter is actually a wave phenomenon, pure wave phenomenon. So if you make a wave packet by sort of interfering lots of waves together, you can work out the acceleration of the matter. And when you work that out, it's quite a tough calculation. You get the same term here. And what this is saying is the acceleration of matter, here it goes, g, 9.8 meters per second squared, in this theory is the same as the acceleration of space. Now let me tell you what's going on in this room here. The space direction is coming from the south. It's about 20 degrees on average from due south. And I've just checked on my iPhone compass. South is down there. and it's coming up around about at this direction. Okay? And as the Earth rotates, it's relatively fixed relative to the stars. And as the Earth rotates, you get the Earth rotation effect that shows up. It also fluctuates and whatever. And the acceleration of matter is the acceleration of space as it goes through this room. The Earth is slightly changing the speed of space, and that causes this effect. Again, all the experiments so far are very complicated. You have to ask NASA to repeat the experiments, and I won't answer the email, of course. So you've got to move on.
You've sent them
Many. Okay. Let me go to LIGO. This is the LIGO attempt to measure gravitational waves. And people have been trying to detect the Einstein gravitational waves, which are meant to be the ripples in space-time, and they're supposed to travel at the speed of light, and they're supposed to be incredibly weak and only produced now and again by some cataclysmic event like a black hole swallowing up stars. No.
What you were saying is not
after the presentation.
Let him
It's
finish.
Wheeler said. It's not Einstein said.
For some
Yeah.
courtesy.
So let me remind you that this is the Michelson-Morley design, and here they are. LIGO has spent $1 billion making two of these. The arms are now under 4 kilometres long. You can't rotate it, of course. And this is down in Louisiana. This is up in Washington. And here's the design. And we now understand how a Michelson chronometer works. It's got this coefficient out the front called k squared, calibration constant. It's given by this value. And by the way, one of the German experimenters, instead of using air, he used helium, and you get the same result. The refractive index of helium is even smaller, closer to 1.
How do this large scale experiment deduces gravitational waves based on the speed of light?
What they want to do, these are separated across continental America, and what they want to do is pick up some fluctuation in this device, and then the same fluctuation appearing about 10 microseconds later, I think it is, up in Canada or whatever. But they do it in vacuum. At great expense, they pump the air out of the arms. If you pump the air out, it's got zero sensitivity. I pointed this out in 2002 and said this device, which hadn't been completed, it wouldn't work. When they finally turned it on, it didn't work. It cost them $1 billion to do this. And they know about my work and my claims about the Michelson chronometer. And I get feedback from what they tell the intermediary. So Harry Collins is the friend co-worker with Andrew. He knows all these people, and ask them, why are they ignoring my work? And they say, impossible. So anyhow, if they save money by turning off the vacuum pumps, it would work. You can't get them to do it. But there's even simpler ways to do this experiment. And at the moment, they're spending another $500 million, because obviously the gravitational waves are weaker than they thought. So they're spending another $500 million to make it more sensitive. And they're trying to get it finished for next year, which is the centenary of Einstein's general theory of relativity, published in 1915. They're going to be disappointed, because they won't let air in. Anyhow, this thing here is what they should be using. They should be using 2 of these, not 2 of those. This one's $20 each.
Yeah.
And when you say to someone who's just spent $1.5 billion, why don't you do this? They can't, that's out of their mental grasp. It's just too absurd. So I did a whole lot of experiments. I don't have a laboratory. I just run the experiments up and down the office wall of my study at the university. I've just briefly mentioned, this is one in 2006. You send light up through an optical fibre, radio waves through a coaxial cable, and for very subtle reasons, the speed through these is different, and it depends on orientation. You get some result like this over a 24-hour period, and this is at different months of the year. What you can see is the phase is different. That's because of the sidereal effect over a year. The sidereal day doesn't track the solar day. I sent this to I went to a conference. I was allowed to present a paper that was banned from the proceedings. That's strange physics, wasn't it?
That's what this is about?
No.
Okay, sorry.
No, this thing here, here's an oscilloscope. Here's the coaxial cables and the optical fibres. CERN donated the optical fibres. And they sent out $100,000 worth of optical fibres because they didn't need it. I needed 5 metres. They sent out about 100 metres of the stuff, which was left over from when they built the left. It's particle accelerator. And they didn't need it anymore because they had better optical fibres. And these optical fibres are specially constructed to have a very low sensitivity to temperature in terms of the speed of light through the thing. And they sent it out. It required a forklift truck to pick it up, and they soon gave it to me for free. Here's another one I did. Desperate to find a cheap way to measure gravitational waves. Here's the Michelson barometer as Michelson did it, as LIGO is still doing it. Here's one where you have optical fibres. Here's one arm, here's the other. Optical fibres have a refractive index that's very different from that of a gas. And here it is. It would fit in fit in a reasonable pocket. It costs about $200 to make. I've been getting the cost down over time, as you see. And so it's an interferometer. And the interference is where the light from the 2 arms comes in here through what's called a beam joiner. And you get interference between the light, which is in the infrared, in the red. And the 2 light beams come through this where the fibres come close together. The filament, the covering has been peeled away, so you get crosstalk between the 2 fibres. So you get an optical interference, and then you send it off to a photodiode for one of them, and the other one comes out here. And you get a split of the energy in the light between these 2 fibres, and that's how you do the interference experiment. And so then I did another one. I've had a very exciting life in the last 10 years. Right? Here's one. This one here is an improvement. It's got a frequency standard, a rubidium clock. This is an oscilloscope that measures the time difference between the 2 RF signals. And it has 2 different kinds of coaxial cables. So instead of using optical fibres, which are really difficult to work with because of the temperature effects. So here's that, and instead of just having it like that, it's folded back on itself many times, and altogether it's 15 metres of one kind of cable, 15 metres of the other. You have to assemble them, and you have to join the coaxial cables end to end by hand, because I couldn't afford, I had no research funds to buy plugs. So I spent a month joining these together, and here it was tested up in the spare bedroom, make sure it works, before I took it to work, set it up. And again, I'll show you the date, but this is yet another way to detect this effect. So, again. No, it's long taken.
Mysterious data.
No, I pressed the wrong one again. Thank you. So here it is, set up in my office. I'm a very untidy experimentalist, and here's the coaxial cables going backwards and forwards. There's a frequency standard here in the oscilloscope, and here's the data. And this is the difference in travel time between the two circuits. You always have two circuits, and you compare the travel times, because when you subtract them to get the travel time difference, you also tend to subtract temperature effects, because they're locked together. That's why you have all the cables down tightly together. And here is the differences in travel time. And again, the maxima are at 4 hours, and the minimums at 13 hours. Same as Michelson law, same as Miller, same as NASA data, and so forth. And this is the ideal one if the flow of whatever's happening was fixed in direction and speed, but in fact you see all these winds, just like Miller saw in 1925-26. A lot of disturbance in whatever's going past. Okay, so here's another one. And what you can do is you do a Fourier transform, and you look at the amplitude of the Fourier amplitude versus the log of the frequency, and you get a straight line. This is telling you that whatever's going past has what's called a 1/f spectrum. And 1/f spectrum have been known in electronics for about 80 years. Every bit of electronics suffers from 1/f noise. And then this is a little bit able to figure out what it's about. It looks like it's just space going past all the instruments. This is a artistic representation of what I think space looks like. It's got a sort of a quasi-cellular structure, and fractal means that it's got all sorts of sizes there, which is also consistent with a 1/f spectrum. And in each cell, the average speed and direction is slightly different. And this structure is going past us at around about 500 kilometres per second, and it's coming through this room right now. If we had all these other detectors, I could actually measure the speed through here and show you the fluctuations as it went through the room. So, you did that. Then, I have a friend who used to work at my university in Sydney, in Adelaide, and what we decided to do was do a correlation analysis between my detector in my office. Here's the coaxial cables, here's the oscilloscope collecting the data, here's the RF source, and he did the same thing in London. He's not an academic, otherwise he wouldn't be doing it, of course. He knows what's good for him. He owns a private company. And it's orientated like this now because we don't want to study the Earth rotation effect. So these two apparatus are parallel to the spin axis of the Earth. We just want to look at the wave fluctuations, not the rotation of the Earth. I mean, it's a simple thing to do. You just stack it up. And you do that experiment. And then, sorry, I'll go back. Then you do what every good experimentalists do, is you disconnect your sensitive device, this coaxial cable array, and you sort of literally feed the RF signal directly in to the scope into both channels, and you measure the time difference between the two RF signals which are in phase but going to the different channels of a double beam oscilloscope. You've got two separate oscilloscopes. And you do that because you want to measure the signal to noise. How much noise is coming from this, and how much noise or physical effect comes from the cable. It's called the signal to noise ratio. You always try to do that when you do an experiment. So we did that, and these two instruments were connected via the internet. They were synchronized in time down to milliseconds and whatever. And then instead of seeing what I expected to see, I got the shock of my life. Well, I've had a few actually, but this is another one. And that is, when you look at the data from Adelaide, which was in my office there, is in blue, and the one from London is in red, and the one in London has been delayed by 15 seconds, and then they seem to be in phase. The small bits with the small bits. So look at this correlation here. If you put in a 15-second delay, that correlates, and then the space goes out of phase, because between Adelaide and London, you don't always get the same bit of space going past Adelaide and London, because Adelaide and London are quite lined up with that direction that Marcus and Morley and Bill and all the others were saying. Okay? This knocked me off my chair. This I didn't expect to see. Turns out the oscilloscopes were responding in unison with a 15-second delay. This is called 1/f noise in electronics. But it's the space going past through first one instrument, and then it turns up in London.
What's the horizontal time scale?
Oh, these are seconds. This is on a particular day, so this is 15,000 seconds, 15,050 seconds, and this is Greenwich Mean Time. And it's on January the 1st, 2013. Well, I did on that day because it's my birthday. So it's just accidental.
You're measuring noise,
We're just measuring noise,
and you got the same
and
noise in both
and it's been filtered to take out some of the high frequency stuff. So you've got to look at the low frequency stuff. Then you see that both oscilloscopes, separated by 10,000 kilometres,
show the same noise.
are showing the same noise pattern, but with delay. Let's measure.
That's pretty so that's something.
Here we go. Here it is here. This is the digital storage oscilloscope, one in London, one in Adelaide. Here's universal time, Greenwich Mean Time. Here's the travel line time, the delay time between what I see in my scope and what David was seeing in London. And here's sort of starts at about 15 seconds. And as the Earth rotates, the travel time goes longer, and then down again. And you see all this data here. It's got a lot of scattering because space has a lot of structure. Okay, it's not a uniform flow. And what happens at this particular time of the day, well, for this experiment, the travel time between Adelaide and London drops down to about 12 seconds, whereas it's expected to be up here. And this is where space on this particular time goes deeper into the Earth. So this effect here, which I didn't predict, and was shocked to see, is telling us that when the space gets deeper into the Earth, it speeds up. There's some new physics, a new phenomenon. I can speculate what I think is causing it, but I haven't done my homework. Here is where people had some of these devices here, and there happened to be one in Perth and one in London. They were doing an experiment called associated with the Global Consciousness Project, where they have these random event generators. And the data from Perth to London, and there used to be a detector like this in Adelaide, but it stopped. And what you get is a similar sort of effect. And the Adelaide-London data gives a speed of 512 kilometres per second. Right ascension 4.8 hours, declination minus 83 degrees south. When you look at Perth-London from these electronic detectors, you get 528, and at the same time, right ascension 5.3 declination. The same numbers keep cropping up. 127 years after Michaels and Morley. Now we come, I finally figured out why the scope's doing it. I made a guess. It's just some electronic solid state effect in these oscilloscopes. And so here's the ultimate test. You have a little battery. I'll hold it up so you can see it. You have a little battery, 1.5 battery. You have a number of diodes here. You have a resistor here, and this is what's called reverse bias. So these diodes are set up so there should be no current flowing through here. The normal current, electron current, will flow around this way. Oh, sorry, the reverse of diodes, the current will flow. So this is with reverse bias. I'll show you what that means. Here's the picture of it. It's got 5 of these. It's got 2 here. The more you put in, the more sensitive it becomes. Each diode costs you 50 cents. The most expensive part of this experiment is the middle box, $10. It's got a lid on it. I didn't bring the lid to cut down the weight on flight. Okay. And a little battery and a switch and a 10,000 ohm resistor here. And you put it in the metal box to make sure there's no electrical interference, and you get a coaxial cable so there's no electrical interference. And you do this, and it's switched to turn on and off. And so you do that. And this is the theory. Electrons are actually wave phenomena. Here's the diode structure. It's got a P region and an N region. And then here's the electron wave coming through. And in reverse mode, the way you operate this thing, there's a potential energy barrier between these two different kinds of semiconductors. And when the wave comes in, it's partially reflected, partially transmitted. This is what's called quantum tunneling. And the amount of wave that gets through depends on how much energy the wave picks up. And because of this space thing here, the space as it fluctuates raises and lowers the energy of the electron. And the higher the energy of the electron, the more it gets through the barrier. So this is one here that relies on quantum tunneling of electrons through a PN junction. And the electron's energy is responding to the space going past. That's the plate. And this is the Schrodinger equation in space group. The Schrodinger equation's never had space in it. It only ever had a coordinate system. So That's the theory. Here it is set up for a lecture demonstration when the dean's not watching. Here are the two diodes, detectors, one there, just like this one here. They're mounted on a stick. I borrowed it from the chemist, a retort stand. I'm getting experiments down to really cheap value, so I borrow the equipment from the chemist. It's half a metre apart. And here's the two traces on the oscilloscope. Here's another monitor so you can see it. And you can easily measure how long it takes, and this is pointing towards the south celestial pole, roughly speaking. And you get a signal in this one, and about a millionth of a second later you get the same signal in this one. There's a time delay of a millionth of a second. And it does fluctuate. And here are the speeds you get. The average speed at this particular time, February 28th, not so long back, 2014. You can easily measure the direction of the flow. It's coming from the south. The average speed is 474 kilometres per second, and it's fluctuating. These are readings every 1 second, and you can sort of see that you get huge fluctuations. It's like a 20% effect, just like millisol. Bang, bang, bang. So here are the conclusions. So I'm about to round up. My conclusions. They're not universal conclusions, I know that. Okay. Space, and I have a much deeper theory about this, and I've shown you only some of the experimental data, some of the astronomical and geophysical, there's a whole lot of other data which I could have shown you too, but it's a bit of a headache. It's been missing from physics. Space is actually a complicated system. I actually think it's a quantum system. Space is a quantum foam type structure. And it's only geometrical if you don't look too closely at it. Okay? It's been missing from physics for 400 years. Many detection techniques, this is very important. Light speed, radio wave speed, this is NASA data, and now using quantum detectors. A high school student can now do this experiment and measure these speeds. So physics is stuff, because they can't stop the high school students doing it. And the high school students can't be controlled. Okay? They don't know how bad it is to do this experiment. So you have to rebuild all the physics. You get a whole new theory of gravity. You have to extend quantum theory because you've got to put space in. You've got to worry about how quantum waves turn into get localized and become what we call objects. It has black holes that agrees with the black hole data. The way these stars circle the black hole at the center of our galaxy. The black hole form is more complicated than you might have thought. It's different to the Einstein one. Fits that data. There are gravity experiments which involve measuring G, little g as you go down a hole in the ground. It's called the borehole anomaly. That comes out. Rotating galaxies, you get flat rotation curves. You get a standing universe, but no need to fit the data using dark matter and dark energy. And the actual theory of space is more complicated than the one I wrote down. You get bending of light by stars and galaxies. The latest thing to discover is that the fluctuations in these devices over a say, 20-year period coincides with solar flare counts. So the noise level in these things, fluctuations, if you look at a Ripken square signal, fluctuations, that tracks perfectly with the solar flare count. And when you look at the solar flare data and the data from these things, you discover that solar flares always follow about 6 days after there's been a major disturbance in space. And clearly it's upsetting the sun and it has a burst. These things can detect earthquakes. Now time delay, that's been shown by other people. So it detects earthquakes. You can also detect earth vibrations, because the Earth's always vibrating, and one of the main periods of vibration of the Earth is it's like a breathing mode. It's got a period of about 4 minutes or something. You pick that up. And what this is doing, this is not a gravitational, it's not measuring G. This thing is much more sensitive because it's picking up a deeper effect, which is what space is doing, not what G is doing. It's picking up space directly, how space is upsetting the electrons. And also, what you discover is another explanation for the Earth climate effect. Some of your stuff, so if you look interesting, compared to this. What has been known for a long time that solar flare counts correlate with Earth temperatures. The climate people ignore that because they point out, well, you might have these solar flares coming and going, but the extra energy that comes out during the solar flare is insignificant. Okay, so that can't be driving the Earth's climate. But what you find, that nevertheless, trust the data, the Earth's temperature correlates very well with solar flare counts. When the solar flare counts went almost to zero, we had ice ages in the history of life on this planet. So what it's telling you is these fluctuations are creating energy somewhere in the Earth or in the atmosphere or something, I don't know. But there's certainly, just as the wave fluctuations push the energy of the electrons up and down, they do that everywhere. There's nothing special about those electrons. These electrons flying in the diode. So all the electrons that are moving around in the Earth and the atmosphere are having their energy raised and lower, as are the nuclei and so forth. So somehow or other, the Earth's core, not core, but the Earth's body and the atmosphere are trapping that energy in some way. And that's why I think the Earth's climate is tracking solar flares and also tracking the fluctuations in these things. Here we get on to symbology. So space is fundamentally not a piece of geometry. It's a complex dynamical system. It has fractal time-dependent structure. And as I say, definitively measured. Space-time itself doesn't exist because that was based on the fact that all of these experiments should have been null. None of them should have shown any effect. You only get a null experiment if you don't know how Mach interferometer works. And people are still building Mach interferometers with vacuum. LIGO's still got a vacuum Mach interferometer. In Australia, the people who run vacuum mode Mach interferometers and see nothing get huge research grants. I who see something get nothing. It's you know the system. And so one of the problems we have, which is why I find this collection of people so interesting, is how do you end the cold Einstein? It's not going to end too quickly, right? And here's one of the experts on Einstein's theory, and this is from papers he's written and from talks he's given. Anyone doubting Einstein is a crook and a charlatan.
So he's not a those were exactly.
There's one here.
No, those were his exact words.
Christian doesn't understand generally.
He thinks he does. He's the world expert on it.
He is not an expert.
Okay. We agree.
No, because I wrote a paper saying he's wrong and sent to Astrophysics Journal. And he argued for 4.5 years. He lost.
So we should have.
Yeah, he lost.
So I think that's my last one. Yes, it is. The other thing I should have mentioned, I didn't kind of realise how many people are going to talk about the LA effect. During solar eclipses, these things can pick up disturbances in space that track the solar eclipse moving across the surface of the Earth. Okay? I didn't do the experiments because these things have been around for 18 years. The people collecting the data thought that it had something to do with human consciousness. They're crazy. They were sociologists. Sorry.
We have a paper on.
I've got hundreds of papers. You want a box like this?
Yeah,
I'll send it to you. If you want a copy of any of this stuff, just send me an email. You can figure out my email.
I like to
Contradict. Okay.
to read your paper because I think there's something very valuable inside.
Okay. Okay. There's going to be some talk later about the LA effect during the 2017 solar eclipse. And most of the people who do that experiment, I think the early experiments, are LA pendulum experiments, which I've done. I've seen the pendulums process, and Hector and I were involved in a project from 2005 where we had these pendulums, one in Adelaide and one over in Hector's place. And I stayed up all night with some students and collected data. And this pendulum just started processing and came back. It was just the most dramatic one. I won't say the most dramatic one in my life, but it was very dramatic. But these things can pick it up. And so if you were thinking about sort of encouraging people to do an LA experiment, what you do is you have some of these located, and you just record the noise level of these things, the current fluctuations. And these are cheap. All you need is 2 of these and a USB type oscilloscope recording the data on a laptop.
So you're saying this detects space rather than electrical noise, or electrical noise as a byproduct of the space flowing through?
Right. And the other point is that the quantum randomness that's always been in quantum theory from the days of Born in 1930, that was his interpretation of what the wave function is about. It's a probability theory. What this experiment shows is that the quantum fluctuations are actually totally controlled by space. So there's no randomness in quantum theory, it's in the space going past the device. That's what this
But it can't be
There are
random.
fluctuations in space, not randomness.
Well, it can't be random if you have in London and in.
Well, of course not. But when you have them this close together,
Yes.
you get much cleaner effects because you don't have to worry about the space evolving and changing.
Yes.
And I operate these things 25 centimetres apart, and it just sits in the office, and people come in there and look at it, it blows their minds if they know about the history of physics. The correlations are just perfect.
So, out of this project, we could scatter these things around the world all measure at once.
Yes, and they're already up there. There are 70 of these detectors operated by amateurs around the world who think they're working on global consciousness project. What they've been doing is collecting information on space fluctuations for the last 18 years, which is another way of talking about space fluctuations since it's related to gravity. They've been detecting successfully gravitational waves for the last 18 years. LIGO hasn't yet to detect one. And I think the LIGO people are spending $1.5 billion on that project. It's going to turn out to be one of the biggest scandals in physics. You might know some bigger, more expensive ones, but that one is massive. Not only that, because they were told to do this. They could have a gravitational wave detector working within an hour. Technicians can knock one of these up, two of these, in an hour, including coffee time. I do all this on my kitchen table, much to the disgust of my wife. She says, when are you going to move this program? I say, this is cutting edge physics. Get it out of here. It counts for nothing.
Let me remark something about Clifford wheel.
Okay, more about Clifford. I'll hear this.
We're running out of
We're running out of time.
time. Running out of time.
Okay.